Imagine a man-made object tearing through the night sky at such brutal speeds that the air around it doesn't just part, but shatters and burns into superheated plasma. This extreme velocity beyond normal human imagination is so immense that no early warning system or air defense siren would have enough time to sound before the target is utterly destroyed. This isn't Hollywood science fiction. It's the pure physics of an unstoppable weapon in the modern era. Could such technology truly exist in human hands today? Hello, science enthusiasts. I'm Ethan Walker, and welcome back to our channel, Weep on Science. Many military experts and Western scientists are skeptical of recent claims shaking global geopolitics. A certain nation claims to have created this aerodynamic monster. But here, on Weep on Science, we won't get caught in political rhetoric. Instead, we'll test the truth purely using the undeniable tools of physics, thermodynamics, and material science. Let's dissect this claim from an advanced aerospace engineering perspective. Mach 15. Absorb that number for a moment. That's 15 times the speed of sound, or approximately 5 kilometers per second. Imagine an object moving from one end of a major city to the other in the blink of an eye. At this insane speed, classical aerodynamic laws begin to crumble. The air in front of the missile no longer flows smoothly around its body as with commercial aircraft. Instead, it crashes violently, compresses extremely, and transforms into superheated plasma. This is a real thermodynamic hell. Iran recently claimed that their proud Fattah hypersonic missile not only survives this plasma inferno, but also performs sharp, complex maneuvers while flying. From a physics perspective, is it possible for a metal structure to withstand temperatures equivalent to the sun's surface while sharply changing direction without shattering? Is this a genius leap in material technology or mere exaggerated military propaganda? Before we delve deeper into Fattah, we must define the absolute limit of what is called hypersonic. Unlike supersonic, which merely means faster than sound, hypersonic is a realm where the physics of air itself transforms. The official boundary begins at Mach 5, or about 6,100 kilometers per hour. Why Mach 5? Because at this speed, the main problem for aerospace engineers is no longer how to cut through the air, but how to prevent their vehicle from melting into pure molten metal. Aviation history notes that breaking the sound barrier in the mid-20th century was a monumental achievement, but the sound barrier was merely a matter of pressure waves. In the hypersonic world, the main enemy is the heat barrier. The kinetic energy of an object moving at massive Mach numbers, when it collides with atmospheric air molecules, is instantly converted into heat energy through a process called shock compression. Many mistakenly believe this heat is caused by air friction, like rubbing your hands together. Technically, that's less accurate. At hypersonic speeds, the air in front of the missile doesn't have time to get out of the way. It gets trapped and brutally compressed at the missile's nose. The ideal gas law states that when gas is compressed extremely in a fraction of a second, its temperature skyrockets drastically. This creates temperatures up to 3,000 degrees Celsius at the missile's leading edge. 3,000 degrees Celsius is more than enough to melt steel, titanium, and almost all conventional metal alloys used in standard military aviation. If you flew even the most advanced fighter jet at this speed, its wings and nose would vaporize into dust in seconds. Therefore, designing hypersonic weapons is not just about making a big rocket booster, it's a masterpiece in advanced material science and thermodynamics. This brings us to the fundamental question: why are nations racing to break through this thermodynamic hell barrier? The answer is simple: time and uncertainty. Traditional intercontinental ballistic missiles, or ICBMs, might fly faster in space, but their trajectories curve like a very predictable parabola. Enemy radar systems can calculate where an ICBM will fall even when it's only halfway there. Hypersonics drastically change these rules. Hypersonic weapons, especially glide vehicles or maneuvering ballistic missiles like Fattah, combine the speed of ICBMs with the maneuverability of cruise missiles. They fly in the upper atmosphere, too low to be intercepted by outer space missile defense systems, yet too fast and too high to be chased by traditional anti-aircraft missile systems. They fly in a gray zone, a deadly corridor where no modern defense system is truly designed to operate effectively. Now, let's dissect the anatomy of this weapon system. The Fattah missile is not a single monolithic unit. It's a multi-stage system. The first stage is the booster, a giant launch vehicle. Its function is purely muscle, a solid-fueled rocket designed for a single purpose: to carry the warhead out of the dense lower atmosphere as quickly and efficiently as possible. Without this booster, Achieving Mach 15 is an impossibility. Why solid-fueled? In modern military doctrine, reaction time is everything. Liquid-fueled rockets take hours to fuel before launch, giving enemy spy satellites enough time to detect preparations and conduct a preemptive strike. In contrast, solid-fueled rockets are pre-filled, like giant fireworks. They can be stored in underground bunkers or mobile launch trucks for years and launched within minutes of an order. After the first stage booster exhausts all its fuel and carries the missile to exosphere altitude, the vacuum of space at the edge of space, Newtonian physics takes over. The booster, now a heavy dead weight, is released. This separation process in space is crucial. Explosive bolts detonate with millisecond precision, separating the main warhead, the star of the show, from its booster. Now, the deadly warhead flies freely in the silence of space. At the highest point of its trajectory, or apogee, this warhead experiences no air resistance. It floats in microgravity, accumulating enormous gravitational potential energy. However, this Fattah warhead is not a passive glide vehicle merely relying on gravity to fall back to Earth. It's equipped with a second-stage rocket motor integrated directly into the re-entry vehicle's body. This second-stage rocket motor has not yet been ignited. It awaits the precise moment when Earth's gravity begins to pull the warhead back down. Its speed increases exponentially. From the cold vacuum, it begins to touch the uppermost layers of Earth's atmosphere. This is the re-entry phase. Here, the transition from space physics back to aerodynamic physics occurs brutally and instantaneously. The warhead prepares to dive back, converting its potential energy into terrifying kinetic speed. Welcome to Phase 3, the Plasma Inferno. As the Fattah warhead penetrates the atmosphere at Mach 15, the collision with air molecules becomes so violent that it breaks the chemical bonds of oxygen and nitrogen molecules. Electrons detach from their atoms. Air is no longer gas, but transforms into the fourth state of matter, plasma. This plasma sheath envelops the entire front of the missile, emitting blinding light and generating extreme radiant heat to the missile's surface. If this missile were made of solid steel, it would melt, lose its aerodynamic shape, and shatter into pieces due to the immense dynamic pressure. So how do Iranian engineers, or any aerospace engineers, prevent this warhead from turning into a burned-out artificial meteor? The answer lies in a heat shield using ablative material technology. This isn't a shield that withstands heat, but one that sacrifices itself. Ablative materials work on a basic thermodynamic principle. A change of state absorbs energy. When the surface of this material is exposed to thousands of degrees, it doesn't melt into liquid. Instead, it's designed to sublimate, changing directly from a solid into a gas. This sublimation process requires a tremendous amount of heat energy. What material is capable of this arduous task? Currently, the gold standard in the global hypersonic industry is carbon-carbon composite. This is the same material used on the nose of the space shuttle in Formula One car brake discs, but developed much more extremely. Carbon fibers are woven in a three-dimensional matrix, then filled with additional carbon through a chemical vapor deposition process over months in high-temperature furnaces. The result of this complex manufacturing process is a material that is incredibly light, yet has a melting point far beyond any metal on Earth. Carbon-carbon composites even become stronger as temperature increases, up to a certain limit. Iran's ability to produce precise carbon-carbon components that can withstand asymmetric pressure during re-entry is one of the crucial points determining whether Fattah's claims are real or just an engineering bluff. Surviving the heat is only half the battle. The most terrifying claim of the Fattah missile is its ability to perform evasive maneuvers within the atmosphere. In conventional fighter jets or missiles, turning is done using fins or small wings. But remember our plasma inferno? If you extend small wings into a Mach 15 airflow, the thermal friction at the wingtips will increase exponentially, and the wings will melt off in milliseconds. Without reliable aerodynamic fins, how can Fattah turn? This is where the second-stage rocket motor we discussed earlier comes in. Instead of relying on air to turn, Fattah uses pure rocket physics through a technology called thrust vectoring. The rocket motor inside the warhead ignites, spewing high-pressure exhaust gas backward. But the secret lies in the nozzle, or exhaust outlet. Iran demonstrated that Fattah is equipped with a spherical joint nozzle that can move dynamically. By tilting this nozzle using powerful hydraulic or electric actuators, the direction of the rocket flame can be deflected. Based on Newton's third law of action and reaction, Deflecting the flame downwards will push the missile's tail upwards, which in turn pitches the missile's nose downwards. This thrust vectoring capability allows the warhead to perform trajectory correction maneuvers outside the atmosphere and within the atmosphere. These maneuvers don't need to be very large. At 5 kilometers second, a change in nose angle of just 1 or 2 degrees will result in a change of trajectory hundreds of kilometers from the initial target in a short time. This makes its ballistic trajectory impossible to predict by defense computers. However, there's a heavy price to pay for maneuvering at Mach 50, crushing g-forces. When a high-speed object suddenly turns, inertia tries to keep the object on its straight path. This creates enormous lateral structural pressure on the missile body. The g-forces experienced by the warhead's internal components during evasive maneuvers can reach tens of times Earth's gravity. Humans would pass out at 9G and die at higher levels without special suits. The electronic components, gyroscopes, and nuclear or conventional bomb triggers inside this missile must be designed to withstand mechanical shocks strong enough to shatter concrete. Every circuit must be potted, every bolt's elasticity tolerance calculated. This high-G structural engineering is a top-level state secret. We've discussed how the missile survives heat and how it turns, but how does it know where to go? This is where we encounter one of the most interesting physics paradoxes in hypersonic flight: plasma blackout. Remember the reddish-blue plasma sheath created from ionized air in front of the missile? Plasma is a very dense electrically charged gas. The physical property of this dense plasma is that it acts like an electromagnetic mirror. Radio waves, including GPS signals, satellite communications, and data links from command centers, cannot penetrate this plasma sheath. They are reflected or completely absorbed. This means that during its terminal hypersonic flight phase, the Fattah missile is completely blind and deaf to the outside world. It cannot be controlled by a joystick, it cannot see GPS satellites to correct its position. This blackout phenomenon is exactly the same as the thrilling minutes-long radio contact loss when NASA's Apollo capsules return to Earth. If GPS doesn't work, how can this missile reach its target with the claimed high precision of just a few meters? The answer is a pure autonomous system operating without external signals, the Inertial Navigation System, or INS. It is a masterpiece of quantum physics and classical mechanics. It is essentially a highly sophisticated internal compass and speedometer that mathematically calculates the missile's position based on its own movement from the launch point. The heart of a modern INS is the ring laser gyroscope or fiber optic gyroscope. This device uses 2 laser beams fired in opposite directions within a closed mirror ring. Based on the Sagnac effect, if the missile rotates or turns even slightly, one laser beam will travel a slightly longer distance than the other. This microscopic phase shift between the 2 laser beams is measured by optical sensors, providing extremely precise rotation data to the missile's flight computer. Combined with micromechanical accelerometers that measure linear acceleration, the missile's computer performs a mathematical operation called dead reckoning thousands of times per second. It knows exactly where it is in 3D space without needing to look outside. However, the weakness of INS is drift, or deviation. Over time, small errors in laser measurements will accumulate into large distance errors. Therefore, the quality of the INS determines whether the missile hits a military target or misses and falls in the desert. Now we enter the ultimate question, feared by generals and military strategists worldwide. Can a maneuvering hypersonic missile like Fattah be intercepted and destroyed before reaching its target? To answer this, we must understand how modern air defense systems operate. Shooting down a ballistic missile is often analogized to shooting a bullet with another bullet. This requires a series of processes called the kill chain: detection, tracking, intercept calculation, and launch. Let's start with detection. Early warning radars as large as buildings are designed to scan the horizon for threats, but radar relies on radio waves bouncing back from the target. Remember the reddish-blue plasma sheath? Plasma not only blocks incoming GPS signals, but also absorbs most radar waves hitting it. This acts as a form of natural thermodynamic stealth, significantly reducing the missile's radar cross-section. Although ground radars struggle, infrared satellites in high orbit have an absolute advantage. These satellites don't look for radar reflections, but for heat. And a hypersonic missile flying at Mach 15 shines very brightly in the infrared spectrum, like a giant torch in the night sky. Satellites will detect the missile launch from the first second the booster ignites and continue tracking the plasma heat trail during the atmospheric flight phase, so we can detect it. The main problem lies in tracking and intercept calculation. Defense systems like Patriot, THAAD, or Aegis are designed with the assumption that the target flies in a predictable ballistic trajectory. Defense computers observe the enemy missile's trajectory, calculate forward physics, predict its future meeting point, and launch an interceptor missile to that empty spot in the sky, waiting for the enemy missile to arrive. However, Fattah does not fly in a pure parabolic line. Thanks to its spherical thrust vectoring nozzle, it can change its trajectory mid-flight. Imagine the defense computer has calculated the meeting point and fired an interceptor. Suddenly, the Fattah missile makes a sharp turn. The calculated meeting point becomes invalid. The defense computer must recalculate and issue correction commands to the interceptor missile. This is a high-speed game of cat and mouse. Here, the mathematics of reaction time becomes the biggest enemy of defense systems. At Mach 15, the missile moves 5 kilometers every 1 second. If the Fattah missile is detected at a distance of 100 kilometers, the air defense system has less than 20 seconds before the warhead hits the ground. In those 20 seconds, radar must lock onto the target. Computers must calculate the changing trajectory. Commanders must give launch authorization, and interceptor missiles must launch from their tubes. Another physics problem is the kinematic energy of the interceptor missile itself. Conventional interceptor missiles spend most of their fuel during initial launch to gain altitude. When approaching the target in the final stage of flight, they often glide passively, relying on their remaining kinetic energy to maneuver. If the Fattah missile performs sharp, evasive maneuvers in the final seconds, the energy-depleted interceptor missile will not have enough momentum to turn sharply and follow it. Therefore, intercepting maneuvering hypersonic ballistic missiles is considered the most difficult military technology challenge of the 21st century. This does not mean it's impossible, but the probability of success drastically decreases compared to intercepting a Gulf War-era Scud missile. This forces superpowers to develop directed energy weapons and space-based interceptors as future defenses, triggering a new round of thermodynamic arms race. We have dissected the thermodynamic anatomy, inertial navigation systems, and interception challenges. Now, let's draw an objective conclusion. Is Iran's claim about the Fattah missile capable of Mach 15 and maneuvering fact, or just military propaganda designed to intimidate its geopolitical enemies? Let's separate what's physically possible from what's engineeringly very difficult to prove. Fattah's claimed Mach 15 speed is scientifically plausible. Modern ballistic missiles can reach even higher speeds, and technologies like thrust vectoring and maneuverable re-entry vehicles have existed for decades. From an engineering perspective, the missile's design is based on proven aerospace principles. The real challenge is manufacturing. Producing heat shields that can survive temperatures above 3,000 degrees Celsius and sensors that remain accurate during hypersonic flight requires advanced industrial capabilities. While sanctions may limit access to certain technologies, history shows that technological development can often advance faster than expected.